In this segment, we'll continue our discussion of ARM instruction design, focusing on instructions for loading and storing registers. Now, the format for load register and store register is on the line of the instruction format chart entitled Single Data Transfer. I've got it highlighted in blue here in the notes. Several things are worth noting about that line. First, LDR and STR have a con field, just like every other instruction, and they can be done conditionally. They have fixed bits 0, 1, which distinguishes them from the data processing instructions, which have fixed bits 0, 0. And they have no fewer than 6 one-bit fields, I, P, U, B, W, and L. We'll discuss all of those. They have RN and RD fields that indicate the target register, RD, and the index register, RN. RD, once again, is not the first register in the instruction word, even though it appears first in the assembly instruction. In fact, note that RD is in that same position in quite a number of instructions. And finally, they have a 12-bit offset value. So let's start by looking at those 6 one-bit flags. All of them relate to choices we can make in the assembly instructions for LDR or STR. First, the L flag, last one in the list here, indicates whether the instruction is a load, or it would be 1 if it's a load, or a store, and the flag would be 0 if it's a store. In a sense, it's like the opcode field in the data processing instructions, but it's just got 2 choices, so it's 1 bit. Second, as we saw in an earlier example, they are STRB and LDRB variants that load only 1 byte. The B bit is set to indicate loading of just 1 byte. Third, offset indexing can be positive or negative relative to the address register, but the offset field that we'll look at in a little bit here is purely positive. So a 1 in the U position indicates a positive or upwards offset, and a 0 indicates a negative or downwards offset. The offset is like a sign magnitude value with U as the sign bit, except that 1 indicates positive. And fourth, we saw that the offset could be optionally applied to adjust the value in the address register. That's indicated with a bang or with a post increment, like LDR R0SP, #4. The W bit indicates write back. So that will be set if we are modifying the content of the index register. And fifth, the write back can be done either as a pre-increment or a post-increment, put either inside or outside the brackets. And the P flag for pre-increment actually indicates this. And then finally, sixth, the I flag right here, it's not a 1 again, it's an I, indicates 2 different interpretations of the offset. And that can be either as a single 12-bit n-signed integer, and in that case, when I is 1, that's what you get, and the value then is 0 to 4095, and the U bit, of course, makes that positive or negative. Or the offset field can indicate a register and shift value, as in the data processing operand 2. Now, we haven't seen this in code yet, but we will later in the optimized primes program. Here's a quick example, and it's also in the transcript. This loads R2 from the location specified by SP, but offset by the value in R1, not by a constant, and in addition, that value in R1 is shifted left by 2 bits. So the offset in this case works just like operand 2 in the data processing instructions, and its format is exactly the same. So we come to question 1. What would the 6 bits in the order given in the instruction I, P, U, B, W, L, what would they be for this instruction? Well, to start with, this is a store, not a load, so the L bit will be 0. That's actually the last of the 6 bits, however. It does have a constant offset, so the I bit is 1, saying that it's an immediate or constant value, not a register shift. It is pre-incrementing before writing back, so the P bit would be a 1, and the W bit would also be a 1. It does have a negative offset, so the U bit will be a 0, and it's writing a single byte, so the B bit will be a 1. Putting those in their order in the instruction, we have, therefore, the value 110110 for I, P, U, B, W, and L. Okay, so that covers the load and store register instructions. Let's move on to the load and store multiple instruction format, which is labeled block data transfer on most charts. Now, this is a close relative of the LDR-STR format. The instructions stumfud and loadinfud and all their cousins have this format. The questions that follow will ask you to analyze this format based on what you already know about such instructions. You might want to review the discussion on those in the ARM assembly int module RTS topic. So question 2. Consider all the variants of block transfer instructions. Stumfud, SP bang, LDMEA, SP bang, STMED, FP. Describe as many 2-choice, 1-bit options for this category of instructions that you can. You should be able to come up with 4 in all. So, answering, first, there is the choice of load or store, just as in the load and store register. Second, a full or an empty stack. We have an E or a F in the instruction. Third, increasing or decreasing order. And then fourth, do we save back into the address register or we don't? So, with that list of possibilities, question 3. Examine the diagram for load, store, multiple instructions and make a reasonable guess as to what 4 of the 1-bit fields signify. The 5th will be hard to guess. We'll discuss it briefly below. Also note that an empty stack is effectively a post-increment, while a full stack is effectively a pre-increment. Okay, so the meaning of the LDR-STR bits up here are a good place to start from, a good basis to guess from. I think L is pretty obviously a load or store choice, and W indicates whether or not to write a changed address into the address register. U indicates upward or increasing addresses. If it's 0, that means decreasing addresses. And P, for pre-increment, indicates a full versus an empty stack. Now this leaves the S, or in some charts it's a B flag. We'll discuss privilege levels in a module on operating system concepts later, and this flag will be worth remembering then. Very briefly, the flag loads or stores the program status register, which includes changing privilege state. It's used by the operating system when handling a system call or returning control to a user-written function. Okay, so question 4. The LDR-STR format, up here, indicated an I option and a B flag with a different meaning. Why are those missing in the multiple load store format? Well, the answer is they're not relevant. The I flag tells how to use the 12 offset bits over here in the single data transfer, and we don't have an offset in the block data transfer. The B flag says to load a byte, but the multiple register instructions always load and store full registers. The 12 bits that were devoted to that offset, and also the 4 bits that were used for the destination register, are instead used to indicate which registers to load or to store. And there is 1 bit for each register, 16 in total. Of those 16 bits, the LSB down here indicates register 0, and the MSB indicates register 15, or the program counter. So question 5. STMFD and LDMFD don't let you specify the order in which registers are stored. They must be stored in register number order. Why is this? What would it take to make it possible to specify any register order you want? And is this worth it? Well, the answer is that these 16 bits here can tell us which registers to store, but not the order. To describe an order, we'd need something like 16 4-bit fields, each one giving a register to store. That's definitely not worth it. We've seen plenty of uses of STMFD and LDMFD to create and tear down stack frames, but the instructions are also designed for another purpose. And to see how that works, I'm going to ask a question 6 here. What does the following code do? Well, the two registers R10 and R12 are pointed at two different places in memory. We're using addresses here, equal place 1, equal place 2. And the LDMFD, loads 10 registers with content from 10 successive words at place 1, a total of 40 bytes in all. And then the STMFD instruction copies those words at place 2. Block copying of data, copying large numbers of bytes from one location to another, is a common task in code. Copying a string or an array is an obvious example. But even copying a large struct requires many bytes to be loaded from one place and copied to another. The load, store, multiple instructions are ideally suited to this. They can use as many registers as you have free to suck up a bunch of data from one location and then copy it into another. And just to think a little more about this, question 7, what useful thing happens if we repeat the last two lines from the prior question over and over? Well, the answer is because of the bang modifiers here and here, R10 and R12 increase as they load and store registers, so they're positioned to copy the next 40 bytes and the next. Copying up to 10 words at a time in a loop whose body is just 2 instructions is a lot more efficient than the much larger loop you'd need to do this 1 word at a time. And then question 8. Let's wrap up with a couple more machine language to assembly translations. As for the prior segment, please translate this machine language instruction to binary, then give a field breakdown, then an English description, and then equivalent assembly. And the binary instruction is E9ADFOFO. So, probably a bit of analysis there, but you should have come up with. This is the binary equivalent of that. And here is the field breakdown of the instruction. So we have in English, always execute, an LDM-STM format instruction with pre-increment or full stack behavior, upward, ascending, we'll ignore or not use the S bit, right back, an exclamation point. It is a store, not a load. The target register is 13, or stack pointer. And then the registers to store, again from right to left in ascending order, not R0 or 1 or 2, but R4, R5, R6, R7, and then all the way up to R14, or the link register. And then the assembly instruction should be STMFA, SPBang, and then that list of registers. Okay, and hardly surprising, please do exactly the reverse, starting with this assembly instruction. So answering here in English, we have an execute always, load store multiple, empty stack, increasing addresses, no system bit, no write back, a load, using FP as the base, and storing registers 0, 1, and PC 15. And then breaking that down by fields, and with a meaning for each field. We have always, load store multiple, empty, no pre-increment, therefore a post-increment, that's an empty, upward, no S-bit, no write back, yes on the load, FP is register 11, and then here registers 0 and 1, and 15 the PC. And then translating that into binary and finally hex, we get this. And in the next segment, we'll look at branches and various other instruction formats.